Everybody, I don't know how many people are in the room. Just to get an idea. 30. Okay. So I'm talking about CVMFS, NIX, Lmod, and EasyBuild and Compute Canada. My name is Bart Olderman, and I'm an analyst at McGill HPC Center, which is part of McGill University in Montreal, in Quebec, in Canada. And and then we are cooperating at a provincial level in Calcul, Quebec, and also in a national level in Compute Canada. And this talk is about our new setup in Compute Canada. So okay, good. So we're putting on new, bigger national systems that replace the many smaller local clusters that we have now. And the idea is to give them a common software stack. So if people move from cluster to cluster, they see more or less the same software installed. And we can do that using a distributed file system that will work as long as the systems are more or less similar hardware. But even if they have different hardware, we try to make it. We try to give a consistent set of modules. So what happened in the past couple of years, there was a bit of stagnation within Compute Canada with not so many new clusters coming online, but now there's a push with some new systems coming online. The first one was one at the University of Victoria, which is more a cloud system. And the big ones that are coming online soon, within 2 months, are Cedar and Graham in British Columbia, Vancouver, and in Waterloo in Ontario, and they are both going to be systems that show up in the top 500 with about 30,000 cores and a significant amount of CPUs as well. So we're basically working very hard to get especially Cedar and Graham online in a good state. And after that, we'll have late this year, hopefully, also a new large parallel system called Niagara at the University of Toronto in Ontario. So the first tool we're using is CVMFS, and CVMFS is really just a remote file system, but it's a lot more geared towards software distribution than something like NFS, which works okay locally, but when you try to distribute it, then it is much too synchronized. So the CVMFS or CERN VMFS is originally coming from CERN in Switzerland. You must all be aware of CERN. And for their Large Hadron Collider project, the LHC, they developed a distribution system for the software that deals with that. And the advantage of that is that this distribution layer is redundant and has multiple cache layers. So the distributing server is called the Stratum 0 in CVMFS language, and then the cache distributes to multiple Stratum 1s. And then we have another local squid cache, so that if one of the central servers is failing, we still have our software distributed. And everything happens automatically. So basically, when we push the software out onto CVMFS, it's already within a couple minutes, it will be visible on all the client sites of CVMFS. And they mount that file system read-only via a FUSE file system and user space module. So this is like a picture of what it looks like. We got the repository node right here. Do you see my mouse pointer?
Yes.
Okay. So we have the repository node, which is the place where we build our software, and then we push from the repository node to the Stratum 0 node via an NFS file system, or it could also be an SSHFS file system. And then the Stratum 0 push it to multiple Stratum 1 nodes. In our case, within Canada, we have one Stratum 0 node, and then there's one Stratum 1 node on the east and one on the west, because they're quite geographically far apart, like multiple thousands of kilometers between Vancouver and Newfoundland. It's almost the same distance as flying to Europe. Then from the Stratum 1, we can connect to a Squid node. So the Squid node will cache the files on locally, and from the Squid node, we can mount the files to client nodes. So the idea is that CVMFS, to configure a client, there's a bit of security. You need a public key. Without that key, you cannot mount the file system. Obviously, we don't want the whole world to mount the CVMFS file system. So without the key, you're not getting anywhere. And what we're having is two repositories. One is the soft.computecanada.ca repository. That is the main production file system, and another one, soft.dev, which is for testing. So we can push it first to the dev repository, then see if it works from a remote file system point of view, and then we can test it on, we can make sure it works on the real repository. The next tool we're using is NIX, and NIX is basically what we are using as a convenient way of compiling software that sits in between the OS and the scientific software stack. So it's in effect, it's replacing the RPMs, or if you were using a CentOS or a Red Hat based repository or Debian packages. So it's an abstraction layer between the OS and the scientific software stack. And it includes basically everything apart from the Linux kernel and drivers itself. So we're including, for instance, the glibc. So we prevent issues that users, they go on an outdated Red Hat system and they say, oh, I need an updated glibc, and can you please install it for us? You say, that's a bit hard. So in this case, we control that whole software stack, and we avoid any issues with outdated underlying enterprise software distributions. So we prevent issues with certain things not being installed and having to create modules to basically compensate for outdated software. So we carry all the dependencies of the scientific software stack, and NIX is automatically making all the paths RPaths. So there were a few presentations yesterday that talked about RPaths, so we don't have. So all the paths are RPaths, and technically it's a run path, so LD library path takes precedence. So there's basically two kinds of RPath. One is the old style, which takes precedence no matter what, and the other one is the run path, which is a newer style where the LD library path takes precedence. And both styles have their pros and cons, but it is out of the scope of this talk. We have hundreds of packages support out of the box. So NIX provides an enormous amount of packages, but they're mostly, almost all are open source. So it's basically really an open source software stack. It doesn't gear towards Intel compilers or PGI or what have you. And it doesn't support many of the scientific packages. So most of them are packages that you'll find in any Linux distribution. And so we use a main 16.09 profile that tracks the September 2016 NIX package release. I'll show you a few examples to show you how this really shows up in our directory structure. The other tools we're using are EasyBuild and Lmod. I don't really have to introduce them because I think I'm preaching to the choir here, because everybody knows what EasyBuild and Lmod are in this room. So conceptually, NIX and EasyBuild work at a very high level. They install packages at in a very similar fashion. Is that you take a recipe, which in NIX is called a NIX expression, and in EasyBuild is called an easyconfig. And we perform the builds using these recipes. And for Compute Canada, we've been forking the recipes from NIX and from EasyBuild and putting them on our own GitHub repository. So there's the NIX package fork, and we also made forks for EasyBuild, namely all components, framework, easy blocks, and easy configs. So especially for the framework and EasyBox component of EasyBuild, this is just to make local changes, and especially the framework and EasyBlocks, we intend to contribute them all back, all the changes that we made. For easy configs,
I think we've lost sound again. It's very frustrating. I don't know why. Oh no, you're coming back.
Okay.
Oh yeah, no, it's good.
We're good again? Okay.
Yeah.
Okay, so what we're doing is that many of the more boring packages in EasyBuild, like CMake and IX libraries and the libxml and all these things that are basically replacements for things that are already in any Linux distribution, we don't build them using modules. And so we put them in NIX, and then in EasyBuild we just filter out these dependencies. So, and then there's a certain step-by-step procedure that we're following. We install things on a build server, which we call build-node.computecanada.ca, and then we test it on that build node. We deploy it on a CVMFS dev repository, and then the last step is to put it on the production repository. And should we build software X using NIX or EasyBuild? And basically, it depends on whether it's software performance critical or depends on MPI. Basically, could take advantage of the Intel compiler or depends on any MPI stack we build using EasyBuild. Anything else we usually, unless we have a specific software where we want multiple versions available of the same software, but in that case we can actually choose between NIX and EasyBuild, and we can even still use NIX to build the software and let EasyBuild create a module for it. So that structure I'll explain later. So the idea of using NIX is that we basically, instead of EB, which is for EasyBuild, we use another tool called NIXenv. And these two tools have a lot of similarities in that they both build and install software. But instead of creating modules, NIX just puts software into a NIX user profile. And the expectation of that profile is that you typically have that profile in your path. So usually users have a per default user profile, and from that profile, the software is symlinked. Obviously, it's possible to create, like NIX can create multiple profiles, and you can set up paths to point to those profiles, even using modules. So we take advantage of that later. And it's possible to install packages in a user environment. So in that case, the profile is somewhere under your home folder. Or it's possible to install it globally. And in our case, we use a special NIX user account. We sudo into that account to install software in a global place, which is then exported to CVMFS. And in both cases, the packages are not built under the user's account. They actually are built via a special daemon. It's called the NIX daemon in a special ch root, which keeps the builds more pure in that they don't see the OS packages. So for EasyBuild, you're probably all familiar with this procedure. We use an EB-S to search for packages, and we can also test things in a user's environment. For EasyBuild by using a prefix, or I really have to check out the --= pretend switch as well, because I only recently discovered that it exists, so I need to see what it's doing exactly. Globally, we also use a common user to install things globally. So the idea is that we sudo to an EB user to install things in the central place, and this basically so that the installers know, oh, we're now doing something that's serious, and we're going to mess up the global structure instead of if you don't use sudo, you only can mess up the files in the home folder of the build node. We also have multiple versions So the new clusters will all have Haswell and later processors, but we also intend to be able to use a software stack on older processors. So we have part of the stack that is built using generic optimizations and part using Haswell optimizations, and that we'll put the module files and the software in a slightly different directory location. So I use a wrapper around EasyBuild to set up the correct options. And then finally, this is all very site specific, but just to get you an idea is that we need to deploy things on CVMFS. So how do we do it? We push things to the Stratum 0, and we do that using an rsync and an SSHFS connection to the Stratum 0. And that just means that the Stratum 0 file system is mounted via SSHFS. We start a transaction, so we copy things over, and then either we commit the change or we abort the transaction. And this is all going via sudo commands to make sure this transaction is atomic. So you lock the session, you push it out, and then you either abort or publish the transaction. And then you, after the publish is finished, you lose the lock and somebody else can publish. So just to get an idea what is installed via NIX. So via NIX we install more or less recent versions of a lot of system utilities. So I put a sample of the list until I ran out of screen space. But this is just to get an idea. So we have all the basic OS packages: autoconf, automake, bash, bzon, bzip2, like compression editors. There's Perl and many libraries. The list will probably expand a bit, but notice that we also have things like InfiniPath PSM and various IB related utilities, because they all live in user space. So as long as they are compatible with the driver that's used, we can just install many IB libraries, and then they can talk to the underlying hardware. And if the hardware is not there, then the library is just not used. The OpenMPI is smart enough to only use the libraries that are usable. So this actually means that we can skip a large part of the more mundane EasyBuild modules where other sites would use hidden modules. We just don't have them, because all of these versions are reasonably new, and we don't expect people to need to switch between multiple versions of GNU crap, for instance. So in that sense, what is installed via EasyBuild? So we're now just setting up this stack, and we just have we don't have that many softwares installed, but just to give an idea about what we have installed, it's all more high-level software. So we have things like Chromax and Bowtie and Boost, which depends on MPI. And there's the Python SciPy stack. So this is borrowed in part from the Jülich structure, where the basic Python is more like a Python bear, and then the SciPy stack is in a separate module, which is the bundle of SciPy packages. And much like in Jülich, we have a hierarchical module structure where we have MPI dependent modules, compiler dependent modules, and core modules. So the core modules have actually quite a bit of software, most things that are binary packages, but also obviously we have the tool chains. The tool chains are all hidden, so we only have the tool chains to build things using EasyBuild. We have to specify a tool chain, obviously, but we don't show them to the users. The users just load the compiler, and then they load an MPI variety, and then that expands the module stack. And there's some modules loaded by default, which is the standard env module, which is loaded by default, and that includes the Intel compilers and the OpenMPI. That's basically our main software stack. And we started off with Intel 2017, but then discovered that there was an incompatibility with CUDA, so we're basically sticking to Intel 2016 for our main software stack. So this is all still a work in progress. One thing I made in boldface is this IMKL. I actually installed MKL at the core level, and people are familiar with EasyBuild, but we're always putting the linear algebra at the top level. Like in the Juli setup, the OLF was at the very top. So this comes basically from saying, okay, well, I can install IMKL as a binary package, and the only thing that depends on the toolchain is those interfaces that are built using a special flag actually in the EasyConfig. So we thought, well, why let IMKL depend on MPI if there are many packages that use MKL that don't actually need MPI? So with that idea, I for instance, the NumPy module, NumPy and the whole scientific Python stack that depends on it, typically does not use MPI unless we also include MPI for Pi, obviously. So basically, for that, we want to compile using a toolchain that includes linear algebra and the compiler, but not MPI. So that I contributed back to the framework in terms of having an IIMKL toolchain, and then it can be used to compile the packages. So we have that in EasyBuild 3.1. The upstream easy configs may want to put an IMKL at the compiler level. It's something that sites have to decide for themselves. So I haven't contributed an IIMKL easy config. I should probably do it, but it needs to fit better in the general upstream easy config structure. But in our case, it works, and it simplifies setup because it avoids having duplicate software modules, one for every MPI variety, because just because you have multiple tool chains with multiple MPI varieties, if you push it down to the compiler level, you don't need those. So MKL can be installed at the core level without interfaces, and it's actually still surprisingly usable. So the MKL can be installed at the core level without interfaces, and the only thing that's missing is then the parallel FFTW interfaces and no FFTW2 wrappers, but everything else is there. So it's actually quite useful already, MKL without the interfaces. So we only expect any issues with software that uses parallel FFTW. But for that, we can actually install a separate FFTW as well. So our configuration for EasyBuild, it has a lot of customizations. We have our own module naming scheme based on the one from Juli. Also thanks to Alan for sharing it. And we make a couple changes. So one thing you also observed is that in our modules, we all have lowercase module names. So that we do that via the module naming scheme. And like the hidden modules, so everything's programmed in that Python file. And the other thing is that in order to use existing EasyBuild easy config files without having to edit them, we can put a lot of dependencies in filter depths. So in that case, we can just do EB some easy config file --try toolchain, and as long as the dependencies are in that list, it will just skip them. The other new option we're using is filter nvar equals LD library path, because the NIX LD, which links the EasyBuild software as well, uses our path. So our libraries typically don't have to provide LD library path because everything is our path automatically. There could be a couple exceptions, but I haven't seen any. And in most cases, we could actually work around it by using patch elf to set a run path inside the software. And last but not least, we hide the tool chains. So here's an incomplete list of the main tool chains that we're hiding: IOMPI and IOMKL. The exception of the hidden tool chains are the compiler tool chains that we actually expose. And the main challenge we're running into now building things is that lots of software by default wants to look in /USR. And to avoid that, we have to set up a couple environment variables. And as I go along, I find new environment variables that I need to set in order to make sure that says users not used. So we have the library path and the C path. That's basically set by pretty much any module generated by EasyBuild. But we also need AC local path for things that use autoconf. Package config path, obviously, for things that use package config. And the font config file needs to be reset because otherwise it will use etc fonts and it's not there. CMake has an environment variable CMake prefix path, which basically teaches it to look in the right place. And there's Python path. And this seems to be fairly complete, but it could be, if there's a more exotic build structure, I may need to set up a couple more environment variables. One impure path is the SSL cert file, and which basically borrows it from the main operating system. But what can we do against that? On our build node, we try to minimize the use of devel RPM. So basically, if it can't find the software and user include, then it's not there. So we don't want the software to look in that place by accident. And we haven't set up an R path for EasyBuild. So this is an idea of what these paths look like. So for instance, for the Intel compiler, we had to patch elf the binary, which means to set the R path inside the binary. And if you load the Intel module, we can look at EBroot ICC. This is just the main installer path, and it puts it into EasyBuild software 2017 generic core ICC. So it's a generic software, obviously, because binary only. And so that's where the software is installed. And then the software itself has an R path set, so it looks in $origin, so it looks in the same directory as where it's installed. That's a special $origin setting, and it also needs to look in files in our main 16.09/lib NIX profile. And this NIX profile is our main NIX profile. Which we call the NIX user profile. And then you can see that, for instance, the libm.so.6 is one of the libraries that ICC links to. In turn, is a symbolic link that points to the NIX store. So every software in NIX is eventually stored in a NIX store with a hash followed by the name of the package. And when you upgrade NIX and there's something that changes to the NIX recipe, it regenerates that hash and will rebuild all the dependencies into that NIX store. So anytime we have some kind of CVE, for instance, for glibc or for libSSL or whatever, then and I do a NIX installation, it will figure out all the dependencies, change the hashes, and recompile a whole bunch of software. But the thing is that the profile doesn't change. So if we have EasyBuild linking to that 16.09 profile, it will still work after we address a certain security issue. So then there's a couple novelties, is that we can have EasyBuild wrapping NIX. So the idea is that NIX can install software in a custom profile, for instance, bare Python. So the Python 2.7.13, and like I said, it was multi-generational. So that link, the Python 2.7.13, in turn is a symbolic link to another directory -6 -link, which is like the 6th generation of this Python profile. Then in turn resolves to a user environment with a hash, and then that user environment contains symbolic links into the NIX store. And if we use a command nixenv with a bunch of packages, they get combined into that special profile, the Python 2.7.13 profile. But then I can use EasyBuild to generate a module that has that sets the path and the Python path to that specific path. And I just had to create an easy block to to temporarily change the install directory to basically say, okay, well, I'm calling NIX env inside the EasyBlock, and then I make sure that the module that's generated uses the NIX profile as the EB root Python and all the derivations. So that works quite well, because the two are working in tandem. Like we're installing in NIX, but we have EasyBuild generate a module, and it's all included in a normal module environment. And we can load that module, and if ever Python in NIX is upgraded to 2.7.14 or whatever, then the Python module, the 2.7.13 Python module, will still work because the profile is still there. And with NIX, I can do a garbage collect, but because the garbage collector will see that that profile is still there, it will not delete the underlying links in the NIX store. And we do similar things for GCC. So we create a module for the NIX GCC in the same way. We don't do GCC core because we let GCC core be handled by NIX. So I just eliminated those dependencies on GCC core. Another interesting idea is to have NIX wrapping EasyBuild. This was put out on the mailing list, saying, okay, we can have NIX use EasyBuild to build software, but it's a lot more labor intensive to set it up. The advantage that you then, if you ask NIX to use EasyBuild to build software, you can leverage the knowledge that put in all the easy blocks, so you don't have to translate them to NIX expressions. But it's more complex because NIX is a lot more picky about specifying exactly what dependencies the software needs. So it's a lot more manual labor just to get that started. So it's more of a long-term research project to get that working correctly. Another approach was also done combining NIX with EasyBuild with Robert Schmid, who's in the room as far as I understand. He put up a Git repository called NIX EasyBuild, and we've been borrowing some NIX expressions from there, especially to compile Lmod and the VSC Python packages using NIX. We don't install EasyBuild itself using NIX because we basically have a moving Git repository. So we basically run EasyBuild on the NIX server. EasyBuild on the build server is using a Git checkout directly. So that way, if we push any changes, we can just make it use the Git checkout. But the VSC Python packages, we don't expect to have to change them. So we install those using NIX, and it's more static. So just to conclude the credits, so there's a lot of people work on this. Especially what's responsible is the RSNT, the Research Support National Team for Compute Canada, which has a lot of people all over Canada. It's led by Maxime Voissonneau, who's been in touch with some of you. The team is responsible for setting up this software stack, and also the documentation and the ticketing system and some other things for the responsibilities for the team. So I am the main software coordinator. And Maxime has been helping a lot also with the software stack. He's been doing much of the Lmod and CVMFS configuration. We have some other NIX experts in Compute Canada, like Tyson Whitehead and Sevilla Arfuentes, who has been experimenting with NIX on another compute cluster where users have actually the freedom to install NIX packages in their home folder. So it's more of a standard NIX read-write distribution of NIX that they have installed there. But sometimes when we have issues with NIX, we can ask them for advice. And also my colleague Kwon-Chung Chen, or Casey Chen, who's working with me at McGill, who started combining CVMFS, NIX, and EasyBuild, because he was setting up an OS independent software stack for genomics. And he was starting with Linux from scratch, but he found out that it was very labor intensive to use Linux from scratch, and NIX helped him out a lot by having everything automated. And of course, thanks to EasyBuild, obviously University of Kent, and also Jülich, I took a lot of ideas from Jülich module systems. So I thank Alan and Damien and Marcus and the others at JSC. and also Robert Schmid, who I met last year in Toronto at a Compute Canada meeting. So that concludes my talk. So ask for questions.
Yeah, we'll see if we have some questions in the room here. I can hear myself a little bit, but that's okay. Hands, anyone?
Hey Bart, it's Rob.
Hi Rob.
So I did look at the scripts that you've got. It looks interesting. The challenge that I had, and I was wondering how you're handling it. You said that you're building GCC the NIX way. I tried to build, say FOSS and EasyBuild just kind of naively using the script, and then I think I eventually got it built, but it wouldn't build M4 after that. I think it wasn't really able to build binaries properly, sort of a mess.
Right.
So I was just wondering what's your base FOSS stack look like?
So we do not compile GCC using EasyBuild. We compile GCC using NIX, and then we set up a module using that NIX easy block for GCC. And with that, I can build my software stack.
So I guess, what are the challenges you found, I guess, with that? The wrapper would handle doing the R pathing for you, is that correct?
Yes, the wrapper will just plainly put GCC in a special NIX profile, and EasyBuild will generate a module that just sets up the path to that NIX profile. So, by all intensive purposes, the GCC is just a NIX GCC with a special path.
But you're not using the NIX wrapper.
I'm not using any. EasyBuild calls NIX to install the software.
Okay, I was just wondering about if it ended up with automatic R pathing or anything like that.
Yes. Well, NIX R paths everything, and because EasyBuild just calls NIX to install and doesn't compile anything itself, it's basically TCC, and then TCC calls LD, and yes, it's using the NIX TCC wrapper because it's just the NIX TCC, and the NIX TCC is a wrapper.
And then are you using it to compile Intel stuff as well?
Yes, because what I found out is that Intel compiler will do the right thing automatically. It will figure out to use the TCC LD and links things using that, and it just works.
And do you end up with R paths as a side effect of that?
Yeah.
Okay, that's interesting.
The only thing is that the R paths they link directly into the NIX store, so I have to do some post processing to make sure that they actually R path into our special profile. So that's something that remains to be done.
So I kind of have a question with LD, and because the Intel compiler comes with, was it XILD or something like that? I know that it uses it in certain scenarios, right?
Yes.
But I can't remember what they are, but there are like special cases, right, where it will actually start using XILD over LD. I guess you didn't run into them, or I don't know how often.
No, I haven't. Yeah, I was worried about that myself. I haven't run into them yet, but yeah, we need to watch out for that. So we may have to look into EasyBuild's RPath structure to actually to make sure things are linked correctly, especially when users compile their own software. We want to avoid them linking into the OS glibc.
Hi. So I had a question regarding NKL and putting NKL on at the core level, and that's something that I was thinking also to just as you said, we have SciPy stack sitting on the top of the tool chains, and that's the only reason for it is because of NKL. And it's a question for you, for actually anybody on the room. I wonder if the Scala pack and the FFTW interfaces that ship with NKL, how they differ from the open source ones. If there's really any benefit added to them, or if it's reasonable to just put NKL at the compiler or at the core level, and then have Scala pack and FFTW build on top of those, because that will make some things easier. It looks cleaner to me, but I just don't know if the Scalapack and FFTW interfaces of NKL brings something extra in terms of scalability, performance, or functionality that the open source versions don't. So I don't know, what is your experience with that, or anybody's experience on the room?
Okay, so what I've observed that the MKL binaries already include the Scalapack interfaces. So there's nothing, you know, even if you put MKL at the core, if you use the top level software stack with MPI included, you can still use the MKL Scalapack, because this is all inside the binaries. It's not part of the interface. The only interfaces that are compiled are the parallel FFTW.
Yeah, but what I worry about on that situation is if you have NKL at the core level, and then if you build a FOSS-like toolchain on top, I'm not sure if there will be some interaction between the interfaces that ship with NKL and the ones from the Scalapack model that we will build ourselves. I guess it will be. Oh, you went on chipmunk mode again.
Where were we?
Yes, so
you were answering, I think. Yeah.
Yeah, I was about the MKL. I mean, I won't combine MKL with FOSS. I mean, that's just a different linear algebra stack then. But you could push part of the linear algebra to the compiler level with FOSS by just having open BLAS without the Scalapack for certain packages.
One second.
Hi Bart, this is Kenneth. First of all, thanks for doing the presentation and being so patient with the technical issues we've been having. So
yeah, I'm sorry for running so late with all the technical issues.
No, it's fine. It's working out okay in the end. So,
okay.
One thing I was wondering is, what's your main motivation for looking into this NIX EasyBuild combination? It's very interesting. I've been wanting to dive in something like this myself, but never found the time. And it seems like the combination with NIX is buying you a couple of things. Isolation from the host OS is certainly one thing. That's a big benefit, I think. It's also easier to get more up-to-date things than you would get straight from the OS, like the X11 stack, for example. Maybe a bit easier to keep up to date via NIX than you would via EasyBuild, and certainly via the OS. Is there any other advantages you see, or what was the initial motivation to dive into this?
It's isolation from the OS. Yeah. So this is basically the initial motivation from my colleague Casey, who worked with the genomics stack, that he wanted to run. I think even on at the time on CentOS 5 and CentOS 6. Yeah. At the same time.
So that was the main motivation. But have you seen any other additional advantages now that you have it? That were maybe unexpected, or that they were not fully aware of, that would also be a nice side effect?
Well, there's the RPath that comes for free. That has some advantage, and now having those modules on top of NIX, but and we still have to see how it really plays out. It's still very much in the construction stages at this point.
Yeah, so this is not fully production yet. There's no users on it yet, or?
That's right. Yeah.
Okay. One other question is, so you have the NIX EasyBlock, so you can create modules for whatever is provided via NIX, so EasyBuild can leverage that. I hope you plan to contribute that back as well.
Yeah, the problem is that actually the EasyBlock is public. You can find it in our Compute Canada repository.
Yeah.
The only problem is that it's super site specific at this point, so it just it's sudo -u NIX user, so I have to make it more general to contribute it back.
But there's nothing really other than that. There's nothing that blocks it from being contributed.
No.
Naturally. Yeah. And in the end, would you also be up for writing documentation for this, because it's a very nice setup, I think.
Yeah, we have some documentation, like internal documentation already, like using the build node.
Yeah.
which is a bit put together, and one of my main tasks over the coming week is to polish that. And if I can polish it enough, I can even make like generate public documentation from that.
It would be nice if we can cover that in the EasyBuild documentation itself.
Okay.
Maybe that makes sense. Yeah. All right. Any other questions?
If not, then I think we'll thanks and let you get about your day. I suppose it's 7:30 or something now. More 8.